Muchas gracias. Hello, everyone. Thank you. My name is Matthew Eaton. I'm a fifth-year PhD student at Northwestern University in Chicago, but I had the opportunity of being here in Alicante over the summer, so I'm excited to be back to present to you the data that I did. So I'm an experimentalist, and we deal with a lot of we deal with a lot of very fancy, high-tech equipment, and basically, these scientific instruments typically have their own proprietary software to use to analyze the data. And a lot of times, it doesn't always do exactly what we want, or we may not understand exactly how they analyze the data, and that can be a problem if we want to do specific things. So it becomes beneficial to be able to manipulate, extract the data ourselves in order to get better quality results. And Python is a very helpful tool in order to do that. So the focus of this talk is specifically how I use Python to extract data and analyze the data in atomic force microscopy experiments. And if you don't know what atomic force microscopy is, it's basically you have a nanometer-sized tip that scans across the surface of a material, and interactions between the tip and the sample cause the cantilever to deflect, and that deflection can be detected by a laser that bounces off the back of the cantilever. And that deflection can be recorded as a force displacement curve, and different mechanical properties and other information can be taken from these curves. And because of the nature of the AFM, you can collect these force curves across the entire surface of material and get hundreds or thousands or even tens of thousands of force curves in a single experiment. And sometimes the software that comes with the instrument isn't very good at analyzing the curves. And so what we had to do was try to make our own analysis software. But in order to do that, we had to figure out, okay, what type of information do we want to get from the instrument? So what we're looking for is we want the X data, the displacement data going into the curve, the X data, displacement data coming out of the curve, and similarly the Y deflection data in both directions, as well as the location of each force curve in the experiment. So we have to, in order to do that, we have to look at how the instrument outputs the data. So you can export each force curve data as a text file, and if you open it up, you get this monster over here. So in order to figure out how to get the data, you kind of have to look into it and see, okay, how does it, what type of information do we got? So we start reading through it. Okay, we get the total number of curves in the experiment. That's something we need to know. We have the current curve that it's looking at. We have the direction. This first set of information is going forward. And then we have the signal type. So if we keep looking through the data, we see that the text files gives the data in 3 different types of signals, but we only really care about one. So we're gonna have to ignore all the excess data as well. We have the X and Y coordinates of this force displacement curve, the total number of data points in a specific curve, and then this big block of text here, which turns out corresponds to the Y deflection data. But as we said before, that we're interested in both the X and the Y, but that only seems to have the data for the Y data before it starts to give you the data in the backwards direction. But it turns out it gives you this other information here called the scale X, which is related to the distance between each individual data point in the force curve. So you actually have to take that data and generate your own X, X data yourself. But you would have to go through the files in order to figure that out. So another way to visualize how the text file is presented is you get it gives you a header, it gives you the total number of points, and then gives you the information for each pixel. And then in each pixel, there's 3 different signal types, and then in each signal, there's the forward direction and the backward direction. And so we only care about basically getting data from these blocked off sections, jumping to the next deflection signal, jumping to the next one until we get to the very end. So in order to do that, we have to open the text file and basically start looping through each of the lines of the text file. And then basically use what I call red flags in order to stop at specific lines and say, I want this. So in order to get the total number of points, we use a starts with attribute and say, hey, when it reads points, this is what the data we want to extract. So we do that, and then when we want to start getting the the actual data we're interested in, we have to get a big block of text for the single pixel that starts at when it says deflection and ends when it starts the second signal type. So we save that as a whole section, and then we loop through that section in order to get all our data from both the forward direction and the backward direction. And so we can do that multiple times until we get all the information. We can then store it as a dictionary, and then store it, I store it as using Python's pickle model, which is a way that easily stores Python objects in a way that you can access them later. And you basically just use pickle.dump with your file you want to save, and then in the name of the pickle file, and then to access it later in a different Python script, you do pickle.load. And it's a pretty convenient way to store and access information in Python. So once we have all this data, we can then, okay, now we want to analyze this data. So I won't go too much into detail with why all this information is interesting, but for me as an experimentalist, when I look at a force curve like this, the type of I can get a lot of different information about the material. And I want to extract, okay, the maximum force and use that to calculate the material hardness. I'd want to fit the loading curve to this contact mechanical equation at the top, and by having this fitting function, I can actually use that as a way to filter out bad curves if it doesn't fit the data that well. I also want the slope of the unloading curve. I can get mechanical property data from that, and I also want to know how much of the data it's actually sampling in order to get that slope as well. A big one is this contact point. Where does the tip initially come in contact with the sample? How do I detect that? And then finally, where the tick pulls out of the sample, or the residual depth, and I can get some information about the material plasticity. And finally, I'm also interested about the area under the curve, because that gives us material dissipation property. And you can easily calculate that using this Numpy function, numpy.trapz, and you can subtract the unloading curve from the loading curve there to get that area. So like I said, one of the most pivotal things we need to find is this initial point of contact of the force curve here. And the best way to do that is to detect when you see a change in slope. But if you just go ahead and use the gradient function, you usually get a very noisy response when there's a lot of data in the curve. So the best way to do that is to filter out your data to get a much smoother curve, and then apply the gradient function. And you can get a plot of the gradient like here. And as you can see, you can still get some weird stuff happening from getting the gradient here, so you have to figure out a way to ignore all those points. But once you detect a sharp change in the gradient, you can say that's where the tip comes in contact with the surface. And yeah, so once you do that for each of the curves, you can get a whole bunch of mechanical property data across the whole image. But how can me easily look at all that data to evaluate it without having to click and look at every single curve individually? And basically what I want to do is create a two-dimensional array that shows all these mechanical properties. And I do that using this matplotlib.pyplot.pcolormesh. And you get a nice looking plot that looks like this, where each of the colors represent each of the mechanical properties. And on the X and Y axis, it tells you how, it gives you all the location information. But what I got from the text file was the location of each of the pixels in the center. However, when you use this pcolormesh function, you're not actually plotting the location of the center of the pixel, you're actually plotting the vertices like this. And so since I only have the information of the location of the center, I have to kind of do some math in order to calculate the whole take into account the size of the pixel. And you can calculate the width pretty easily if you know the length, entire length, and the number of points you have. So basically, if your matrix is an n by n array, your length axes for the first two parameters in your pcolormesh need to be n+1 linear arrays. Yeah, so then you can get this pretty easily. And that tells you a lot about the mechanical properties. You can look at all different types of properties and get these nice colorful images here for each of the important information that you want to check out. But like I said, each one of these points corresponds to a force curve. And so if I have some weird thing going on here that I want to investigate, how can I know what happened there? So what I wanted to do is okay, so if I'm looking at this plot here, and I want to see, okay, what's the corresponding force curve, I want to be able to click it and have the force curve pop up. So I want to make this map interactive. And then when I click another one, I want it to go, the next one to pop up, and the mark on the image to go away and pop up where I clicked. And I use that using what is known as a pick event. But in order to get this pick event, I need to basically overlay another mesh over the P color mesh that I have. And I do that because I want to be able to get the index for the XY coordinates of the center of the pixel, where I only inputted the vertices of the matrix. So I use this function called numpy.meshGrid, and basically what that does, you have your X and Y points for each of the center. It basically, the X and Y are 1D arrays. It basically makes two 2D arrays that gives you the X and Y indices at each point in the two-dimensional array. And then once I do that, I use the flatten attribute to kind of turn that 2D array into a one-dimensional n-squared array, and then I get a single, I get two one-dimensional arrays where a single index will give me the both X and Y coordinates of the image, as well as the corresponding index that's related to the mechanical property data. So once I have that, I can overlay this mesh over the same P color mesh, and then I want to set it to invisible because I don't want to see it. So that's why I set invisible false. And at first I have to set this picker, which is kind of like a tolerance. So 5 is like, it gives you like 5 points around the center that it will respond to. And then I connect the figure using this figure.canvas MPL connect and to a pick event, which means respond to the click, and then on pick, which is a name of a function that corresponds with that command. So I also have to define a function that will respond to this event, and in that function, I basically can call an index by using event.ind, and that will give me the index where that was clicked on the screen. Yeah. So now that I have all this data for a single scan, it gets more complex when I have a sample with multiple scans, and each scan has multiple data points per scan, and there are several different samples. So how can I look at all this data intuitively and get some information about that? So one of the ways is to do a stacked histogram, which each scan in a single image is a different color, so I can see, okay, in this one I have kind of 2 different peaks, but one peak is only from one scan, and all the rest kind of are slightly higher in that response. Another way you can look at it is with a box plot, which basically is kind of looking at the histogram from the top, and it kind of shows you the extent of your property. So it's, in this case, since I have 6 different scans there, this kind of shows me each scan individually and how their data is spread, as well as all the data put together in a single plot. And this makes it easy when you have multiple materials that you want to kind of like look at different trends in the data. So here, if I'm looking at materials with different concentrations of a filler, I can see that generally there's an increase in this mechanical property, which is a little harder to see by looking at 6 different box plots. But yeah, so basically I developed the code for extracting data from AFM, an AFM instrument to loop through all the data and get the relevant information. I also showed how we created a 2D interactive mechanical property map that allows us to inspect data from a scan, and as well as a way to visualize our large amounts of data in a way that helps us better understand that the proprietary software doesn't really do that well. That's it. Thank you.